Welcome to the deep dive. Forget scrolling through endless articles. You've given us your sources, and we're here to extract the core insights just for you.
Yeah, think of it as your personal briefing.
Exactly. Consider this your personal, well, acceleration into understanding a really interesting bit of physics.
And we've gone through quite a bit educational stuff, some real-world examples too, to boil it down.
Today, we're diving into vertical projectile motion in one dimension.
Right?
Now, that might sound a bit technical, maybe a little jargony, but it's really about something pretty straightforward.
Totally. It's just how objects move when you throw them straight up or drop them straight down.
Yeah, like think about tossing a ball up, catching it, or less fun, dropping your phone. That's basically what we're talking about.
And our mission today is, well, to make the principles behind this motion, including free fall, really clear and engaging without getting bogged down in, excessive detail.
Okay, let's unpack this then.
Yeah.
First things first.
Mhm.
What exactly do we mean by a projectile? What makes something a projectile?
A projectile, well, in simple terms, it's just any object that's moving through the air, and the main force acting on it is gravity.
Okay, so it's been like thrown or launched somehow.
Exactly. It's been projected, right?
No.
And then gravity pretty much takes over dictating its path. That initial push or release is key.
Got it. And where does free fall fit in? Is that the same thing or?
It's a really important type of projectile motion. Free fall is when gravity is literally the only force we're considering acting on the object.
Ah, okay. So no air resistance, things like that.
Exactly. Now, obviously, in the real world, air resistance is almost always there. Sometimes it matters a lot. But, for understanding the basics, the materials we looked at mostly ignore it. It simplifies the picture.
Right. So gravity is the big player here, the main influence in vertical projectile motion.
Absolutely. It's all about the acceleration due to gravity. And near Earth, that acceleration is constant, remarkably so. And here's the crucial bit. It always acts downwards.
Always down, even if the object is moving up.
Yes. Even if you throw something upwards really hard, gravity starts pulling it back down the instant it leaves your hand. There's no, grace period.
Huh, okay. Always downwards. That feels important.
Yeah.
So if I toss a ball straight up, gravity is working against it on the way up.
Right. It's slowing it down, decelerating it.
And then helping it on the way down.
Precisely. It's accelerating it downwards. That constant downward pull causes that continuous change in the ball's velocity. Upwards velocity decreases, downwards velocity increases. Well, the speed increases downwards.
Okay. Now the sources mentioned equations of motion. Oh. Does this mean lots of math?
Aha. Well, we don't need to get lost in deriving them here, but understanding what they do is useful. They're basically mathematical tools, relationships that link things together.
Link what things?
Things like displacement, how far it's moved, its initial velocity, so how fast it started, its final velocity at any point in time, acceleration, which is gravity here, and time itself.
So knowing some of those, the equations let you figure out the others, like a code breaker for the motion.
Kind of, yeah. For example, one simple one says the final velocity, if you just drop something, is just gravity's acceleration multiplied by how long it's been falling. V equals g times t.
VGT.
Okay, it shows that direct link. The longer it falls, the faster it goes. And generally, if say 3 of those key variables, you can often use these equations to find the missing one.
Okay, so the math gives us the numbers, precision. But the sources also talked a lot about visualizing this with graphs. Why graphs?
Graphs are just fantastic for seeing the motion over time. They give you a visual story. We usually look at 3 main types: position versus time, velocity versus time, and acceleration versus time.
Yeah.
Each gives you a slightly different angle on what's happening.
Okay, let's take the simplest one. Dropping something, free fall. What do those graphs look like?
Okay, so for a dropped object, position versus time, it's a curve. It gets steeper and steeper as time goes on. It's actually half a parabola.
Steeper, meaning it's covering more ground, faster.
Exactly. Shows it speeding up. Then velocity versus time. That one's simpler. It's just a straight line sloping downwards.
Straight line means constant acceleration.
You got it. Constant slope means constant acceleration. And since it's speeding up downwards, the slope is negative. And acceleration versus time, that's the easiest one.
Let me guess. Flat line.
Flat horizontal line, yeah. Below the 0 axis, showing that constant negative, meaning downward acceleration due to gravity.
Okay. Now, what if we throw the ball up? How do the graphs change then? That seems more complicated.
It is a bit more involved, but the graphs tell the story beautifully. Position versus time is still a parabola, but now it's an arc, right? goes up, reaches a peak,
The maximum
a
heights.
maximum height, yeah, then comes back down. It opens downwards.
Velocity versus time, it starts going up.
So it starts with a positive velocity, right? Upwards. But gravity's pulling down, so that graph is a straight line sloping downwards. It crosses zero velocity right at the peak height.
Where it stops for an instant.
Exactly. And then the line continues downwards into negative velocity values as the ball speeds up, coming back down. Same constant negative slope the whole time.
And acceleration.
Still the same.
Still exactly the same. That's the mind bender for some people. Even at the very top, when velocity is zero for that split second, the acceleration is still constant and downwards. Gravity doesn't switch off.
Wow. Okay. That constant downward acceleration, no matter what the velocity is doing, that's fundamental.
Absolutely.
Yeah.
Gravity's pull is relentless,
Yeah.
always towards Earth. That's why the velocity changes so predictably on that graph.
Okay, let's connect this to, like, actual things happening. Dropping something seems pretty clear now.
Yeah, simplest case. Initial velocity is zero, gravity takes over, VD tells you how fast it's going. Pure free fall, basically.
And throwing something up.
You give it that initial upward kick, that velocity, but gravity immediately starts fighting it, slowing it down, brings it to that momentary stop at the peak.
Zero velocity. Zero velocity, then pulls it back down, speeding it up in the downward direction. And interestingly, ignoring air resistance, the time going up to the peak is the same as the time coming back down to the starting height. It's symmetric.
Huh. Okay. What about that hot air balloon example? That sounded intriguing.
Yeah, that's a good one for thinking about initial conditions. So imagine a balloon just hovering, stationary. If you drop something...
Initial velocity is zero. Easy.
Right. But what if the balloon is steadily rising, say moving upwards at 2 meters per second, and then you release the object?
So the object is already moving upwards at 2 meters per second when you let go.
Precisely. Relative to the ground, its initial velocity isn't zero, it's the balloon's velocity. So it'll actually travel up a tiny bit further before gravity wins and pulls it back down.
That makes total sense. The initial state matters. So what about sports? I imagine this is huge in sports.
Oh, absolutely. Crucial. Think about basketball. Shooting a hoop involves getting that arc just right, which is all projectile motion, even if it's not purely vertical.
Right, there's a horizontal part too, usually.
Yeah, which makes it 2D motion, but the vertical part is still governed by exactly what we're talking about. Same with, say, kicking a soccer ball, though spin complicates things there.
The sources mentioned the javelin throw specifically. Why is that a good example?
It's almost a perfect showcase. Athletes are literally trying to optimize the launch angle and initial speed to get the maximum distance.
They're fighting gravity the whole way.
They are. They need enough upward velocity component to give it hang time, but also enough horizontal velocity to cover distance. It's a trade-off, all dictated by gravity pulling that javelin down in that parabolic arc. Physics in action.
Okay, so we've got the basics, gravity's role, equations as tools, graphs as visual aids, and some real examples.
Yeah.
How does this tie into, like, the bigger picture in physics? The sources mentioned other laws.
Right. It doesn't exist in a vacuum. It's a direct consequence of more fundamental laws, especially Newton's second law. You know, F net equals ma.
Net force equals mass times acceleration.
Yeah. So in our simplified freefall model, the only force in the vertical direction is gravity. That's the net force. And that force causes the acceleration, A, which is G, the acceleration due to gravity.
So F maybe is basically Newton's second law applied here.
Exactly. If there were other forces, like significant air resistance, the net force would be different, and so the acceleration wouldn't be constant G. The motion would change.
And what about energy? How does that perspective fit?
That's another great way to look at it. Energy conservation. When you throw a ball up, you give it kinetic energy of motion.
Okay.
As it rises, gravity does negative work on it, slowing it down. That kinetic energy gets converted into gravitational potential energy stored due to its height.
So energy changes form.
Yes. At the peak, kinetic energy is momentarily zero if we ignore horizontal motion, and potential energy is maximum. Then, as it falls, potential energy converts back into kinetic energy and it speeds up again. The total mechanical energy, kinetic plus potential, stays constant if we ignore air resistance.
Right. The work-energy theorem connects the work done by gravity to these changes in kinetic energy.
Precisely. Two different powerful ways, forces and energy, to analyze the same motion.
Okay, this has been really clarifying. So if you had to boil down, what are the absolute key things our listeners should take away from this?
I'd say, 1, vertical motion near Earth is ruled by constant downward acceleration due to gravity. Remember G.
Always down.
Always down. 2, a projectile is just something moving under gravity's influence after being launched. Free fall is the pure gravity-only case. 3, equations help us calculate the details, and graphs help us visualize what's happening to position and velocity over time.
And it's everywhere.
It really is. Dropping keys, a basketball shot, even just jumping up and down. It's not just textbook stuff. It's fundamental to how things move around us. And it all stems back to Newton's laws and energy principles.
It definitely gives you a new lens to see everyday things through.
That's the goal. Physics provides that deeper understanding.
Okay, here's a final thought for you, the listener, to chew on. Think about something like a bouncing ball. Now, obviously, the bounce itself, the impact with the ground, that introduces other forces, it gets more complex.
Yeah, the collision is a whole other interaction.
Right. But what about the parts between the bounces? When the ball is flying up or falling back down, how did the principles we just talked about, constant downward acceleration, the changing velocity, the energy shifts, how do they still apply perfectly during those airborne phases?
That's a great exercise. Start watching things bounce or things being thrown. See if you can spot the projectile motion segments and mentally apply what we've discussed.
You might start seeing parabolas everywhere. Thanks so much for joining us for this deep dive.
Hope it helped clear things up.